Okay, we're section 3-4. Got lots of problems in this section. So we're going to start on problem number 12, which are solving for x. And basically what you'd have to do here is you have to use the properties of logarithms and the inverse relationship between logarithms and exponential functions to solve for x. So there's sometimes a couple ways to do this. And when we use logarithms, we're just going to use natural logarithms to use the properties of logarithms. So one way to solve this problem would be to rewrite this 4 as 8 to some power, and then you would set the powers equal to each other. So that might be, let's do it two ways here. Let's see if we can figure out how you would do that. And or another way you can think about it is I could rewrite 8 as 2 cubed. So you'd have 2 cubed raised to the x power, and then you'd have 4 would be 2 squared, and then you can multiply the exponents together. So you get 2 to the 3x is equal to 2 to the second power. And once you have the same base, then you can just set the exponents equal to each other and then solve for x. You get x is 2/3. So that, and if you think about it, what you have is 8 to the, you'd have the cube root of 8 squared. That's what 8 to the 2/3 power would be. And the cube root of 8 is 2. So then you'd have 2 squared, which is 4. That's one way to do it. Another way to do it is to take the natural log of both sides. So you'd have the natural log of 8 to the x power is equal to the natural log of 4. And then you use the properties of logarithms to take the exponent out. And then you could solve for x, which would be the natural log of 4 divided by the natural log of 8. And if you do that in your calculator, natural log of 4 divided by the natural log of 8, you'll get 0.666, which is 2/3. So this is the easier way to solve these problems, but sometimes you can use more than one way to solve these things. Okay. So the next one we have is 3/4 to the x power is equal to 27 divided by 64. And I think what they're wanting you to do is to rewrite this as 3/4 cubed. So if you take 3 cubed, you get 27, 4 cubed, you get 64. You can see I've got the same base now, and so x is equal to 3. That would be one way of doing it. Or you could do what I did just a second ago. You'd have the natural log of 3/4 to the x power is the natural log of 27 over 64. You take the exponent out using the exponential property. And then you would divide both sides by this. And if you plug that into your calculator, you'd get the natural log of 27 divided by 64 divided by the natural log of the root of 3 divided by 4. And I get 3. which is the same answer I got up there. Okay, 17. The natural log of x minus the natural log of 2 equals 0. So what could we do here? Well, you could do it a couple of ways. You could use the property of logarithms to say the natural log of x over 2 is equal to 0. And one way would be to the natural log of 1 is 0, so I could write those both as natural logs, and then you could set the arguments equal to each other. So you'd have x over 2 is 1, or x is equal to 2. Or you could just think, well, to get 0, I have to have the argument of the logarithms to be the same. So the x has to be 2, so the natural log of 2 minus the natural log of 2 is 0. That also does it. Okay, 19 e to the x equals 2. So this is where the first way I've talked about, if you take the natural log of e to the x and you take the natural log of 2, so we take the natural log of both sides. The natural log of e to the x is x, because they're inverse functions, or you can take the x out. The exponent becomes the constant in front. And the natural log of e is 1, because this is the log to the base e, so natural log of e is 1. So you just get x equals the natural log of 2, and the natural log of 2 is 0.693. And so if you took, just to check it, if you take e to the 0.693, just use your calculator, so e to the 0.693 power, you're going to get approximately 2. You get 1.9997, and that's because there's more decimals here. Okay, 21. The natural log of x equals -1. Just kind of as a thought thing here. The natural log function looks like this. Comes up from negative infinity, goes through here. So, and this is x, and this is the natural log of x. So you can see when the natural log of x equals -1, your answer should, your x value should be between 0 and 1. So what we do is we use the inverse properties of logarithms and exponents, but in this case we say e to the natural log of x and e to the -1 are equal to each other, because if you have the same exponent with a common base, then you can have the same result. Well, e to the natural log of x is x, and e to the -1 power is 1 over e. So 1, either way, I'll just do e to the -1 power. So if you just go to e to the x and then put in -1, you'll get 0.368. And that fits our, what we thought was the right approach. Okay, 24 log to the base 5 of x equals -3. So anytime you have one of these where there's a log that's other than the natural log or log to the base 10, you have to use the change of base formula. So what that says is the natural log of x divided by the natural log of the base is equal to -3. So then the natural log of x is -3 times the natural log of 5. And one way of doing this is you could take this exponent inside. So you get the natural log of 5 to the -3 power. So that would be one way of doing it. And then you could evaluate, well, the arguments have to be the same. So you get x is equal to 5 to the -3 power, which is 1 over 5 to the 3rd power, which is 1 over 125. Okay, so that would be one way of doing it. The other way would be to say you have e to the natural log of x is equal to negative e to the negative 3 times the natural log of 5, and e to the natural log of x is just x. And then we can do the right-hand side. So we take e to the negative 3 times the natural log of 5, and we get 0.008. Well, 1 divided by 125 in decimal form is 0.008. Okay, next one. Approximate the point of intersection of the graphs. So what you do in this case is to find the point of intersection of any two graphs is you just set the two functions equal to each other. So you get 2 to the x is equal to 8. One way of solving this would be to rewrite 8 as 2 cubed, and so that we got the same base, and then you set the exponents equal to each other. So you'd have x equals 3, and then you'd have to find the y value. So it's actually 3 comma 8, because if you plug that back in here, you'll get, so the corresponding y value would be 2 to the third power, which is 8. So the point of intersection would be the point 8 comma 3 comma 8. The other way of doing it would be to take the natural log of both sides and take the exponent out, and then divide by the natural log of 2 to solve for x. And if you do that, the natural log of 8 divided by the natural log of 2 on your calculator, you get 3. Okay, 29. So we're looking for the point of intersection here. Log to the base 3 of x equals 2. So what are we going to do? We're going to use the change of base formula. So we'll say that's equal to the natural log of x divided by the natural log of 3. Then we multiply both sides by the natural log of 3. So we get 2 natural log of 3 on the right-hand side. We could move the exponent, the coefficient inside. And at that point, you can just set the arguments the same. So you get x equals 9. And then the corresponding y value is going to be 2, because it's always 2. Now, again, the second way is you can go from this part, and you'd have e to the natural log of x is equal to e to the 2 times the natural log of 3. E to the natural log of x is x. And then you could, on your calculator, e to the 2 times the natural log of 3, and you get 9, which is the same answer we got over here. Okay, so that was 29. 31. Okay, solve the exponential equations algebraically. Approximate the results 3 decimal places. 4 times 3 to the x is equal to 20. So in these problems, you can't use the second approach. You can't use the first approach, use the second approach. So we're going to isolate the exponential part, which is 3 to the x. So we're going to divide 20 by 4, which is 5. Then you take the natural log of 3 times 3 to the x is equal to the natural log of 5. Use the properties of logarithms to bring the x out. And divide by the natural log of 3. And so the natural log of 5 divided by the natural log of 3 is 1.465. So if you go back to the original equation, you take 3 to the 1.465, which is 5 times 4, you get 20. So that's true. So I'm checking my answer. Okay, 34. 4e to the x is equal to 91. Again, divide both sides by 4. And 91 divided by 4 is 22.75. Then you take the natural log of e to the x is equal to the natural log of 22.75. In this case, again, you bring the exponent out. And the natural log of e is 1, so you just get x is equal to the natural log of 22.75, which is 3.124. 25, I guess, officially. So if we go back to the original equation, e to the 3.125 power is 22.75 times 4 gives you 91 with some other stuff because I only went out to 4 digits here. So okay, what are we going next? 35. 35 is e to the x minus 9 equals 19. So we add 9 to both sides, and then we take the natural log. Natural log of e to the x. I'm just going to, the natural log of e to the x is just x. So you get x is equal to the natural log of 28. Natural log of 28 is 3.33. Let's just check it again. So e to the 3.33 is equal to 27.93 minus 9 is 18.983. So again, since I went out to just 3 decimal points, I don't get exactly the same answer, but I get pretty close, which is what you'd expect when using approximation. Okay, 38. 6 to the 5x is equal to 5,000. The natural log of 6 to the 5x equals the natural log of 5,000. So we take the natural log of both sides. You take the exponent out, so you get 5x times the natural log of 6 is equal to the natural log of 5,000. Divide both sides by 5 times the natural log of 6, which is what I have on the left-hand side. And x is, so the natural log of 5,000 is 6.8517. Divide by 5 and divide by the natural log of 6. And I get 0.9507. So again, 6 raised to the 5 times 0.9507 is 4,999.7. $40. 4 to the minus 3x equals 0.10. The natural log of 4 to the minus 3x is equal to the natural log of 0.10. bring the exponent out. Divide by -3 times the natural log of 4x to solve for x. The natural log of 0.10 divided by -3 times the natural log of 4. So the natural log of 0.1 is -2.3. Divide by -3 and divide by the natural log of 4. And I get 0.5537. So if I plug that back in, I'll have 4 raised to the -3 times 0.5537. And I should get 0.1, which I do. 43. 2 to the 3 minus x equals 565. Okay, the natural log of 2 to the 3 minus x is equal to the natural log of 565. Take the exponent out. 3 minus x times the natural log of 2 is equal to the natural log of 565. Divide by the natural log of 2. Then you'd subtract 3 from both sides. And then you would change the sign. So x is equal to 3 minus the natural log of 565 divided by the natural log of 2. So 3 minus natural log of 565 divided by the natural log of 2 is -6.142. Okay, so if we take 2 and raise it to the 3 minus a -6.142 power, which is going to be to the positive 9.142, gives you 564.95. So we got 3 times 5 to the x minus 1 is equal to 21. So divide both sides by 3. 21 divided by 3 is 7. Then you take the natural log of both sides. Take the exponent out. Divide by the natural log of 5. And add 1 to both sides. So x is 1 plus the natural log of 7 divided by the natural log of 5. Plug it in the calculator. 1 plus the natural log of 7 divided by the natural log of 5. And I get 2.209. If I go back here and plug it in, if I have 3 times 5 raised to the 2.20906 minus 1, I should get 21, which I do. E to the 2x equals 50. Take the natural log of both sides. Take the exponent out. So the natural log of e is 1. So you get 2x is equal to 50. X is equal to 25. Something's wrong there. I got it. Yep. It's like that one way too big. I forgot this is the natural log of 50. So x is equal to the natural log of 50 divided by 2. 1.956. So if I go back to the original equation and I say e to the 2 times 1.956, I get 49.999. $53. 7 minus 2e to the x equals 5. So we'll do is we'll subtract 7 from both sides. So 5 minus 7 is negative 2. Divide by negative 2. So you get e to the x equals 1. Take the natural log of e to the x and the natural log of 1. But the natural log of 1 is 0. And e to the natural log of e to the x is x. So you get x is equal to 0, which makes sense because if you plug in e to the 0, you'll get 1. 1 times 2 is negative 2. Then you subtract that, so 7 minus 2 is 5. $54. Negative 14 plus 3e to the x equals 11. So we're going to add 14 to the both sides. So we'll get 25. We'll divide by 3, so we'll get 25 thirds. Then we take the natural log of e to the x and the natural log of 25 over 3. The natural log of e to the x is x, and the natural log of 25 divided by 3 is 2.120. Again, go back, plug that in. Negative 14 plus 3 times e to the 2.120 is 11. 56. 8 times 4 to the 6 minus 2x plus 13 is equal to 41. What I need to get is this part by itself. So the first thing I'm going to do is I'm going to subtract 13 from both sides. So that leaves 28. 41 minus 13 is 28. Then you divide both sides by 8. So I get 28 over 8. Then I take the natural log of both sides. Once I get this thing by itself, then I want to use the properties of logarithms to get that exponent into an algebraic situation. So you bring the exponent out, 6 minus 2x times the natural log of 4 is equal to the natural log of 28 divided by 8. Divide both sides by the natural log of 4. Subtract 6 from both sides. Divide by negative 2. Or multiply by negative half, same thing. So we should be able to do that in our calculator. Minus 1 divided by 2, so that's minus 1/2, times left parenthesis, natural log of 28 divided by 8, right parenthesis, divided by the natural log of 4, right parenthesis, minus 6, right parenthesis. And so I get x is equal to 2.548. If I go back to my original equation, I'll have 8 times 4 raised to the 6 minus 2 times 2.548. Okay, so 4 to the 6 minus, okay. And then I have another right parenthesis, so the whole thing gets multiplied by 8 plus 13 is 41. Okay, 5663. Must be a new, oh, we're still doing those. 3,000 divided by 2 plus e to the 2x is equal to 2. Well, one thing I could do is I can take the reciprocal of both sides, like that. And then if I multiply both sides by 3,000, I'll get 3,000 times a half, which is 1,500. Then I'm going to subtract 2 from both sides. That would be 1,498. Then I take the natural log of both sides. That gives me 2x on the left-hand side and the natural log of 1,498. So x is equal to the natural log of 1,498 divided by 2. So that's natural log of 1,498 divided by 2. So I'm dividing the natural log thing by 2, not 1,498 by 2. And I get 3.656. So we go back to the original equation. We'll have 3,000 divided by the quantity 2 plus e to the 2 times 3.656. And I get 1.99998, which is close enough to 2. Okay, 73. Okay, what is these? Use a graphing utility to solve the equation. Approximate the results through decimal places. Verify your result algebraically. Okay, so let's do it algebraically, and then we can check it out on the graph. We'll go the opposite direction. So you get e to the 0.09t is equal to 3. So we take the natural log of e to the 0.09t is equal to the natural log of 3. Natural log of e to something is that something. And we divide by 0.09. Solve for t. So we get the natural log of 3 divided by 0.09, which is 12.21. So let's plot that function. And actually what we're going to plot is we're going to plot e to the 0.09t minus 3. So that's y is equal to that. And what we're looking for is where does this cross the x-axis. Okay. So let's go to standard viewing. So what we have is e to the 0.09 times x divided by, or minus, I guess, minus 3. I think that's right. Let's go back. Yeah, e to the 0.09 x minus 3. We plot that. We get that. Our intercept is going to be out here somewhere. What did we say the answer was? 12. Okay. So let's just let's go to the right. And so there's our intersection, which is right there, 12.173, which is close to my 12.21. So what we learned from that is if you have an equation and you want to find the solution, you put everything on one side like this here, and then you plot that function and you look for the x-intercept. And that gives you the solution to that equation. Okay, 79. Solve the logarithmic equation algebraically. Approximate the results to 3. So these are, the previous ones were exponential equations. These are logarithmic equations, but they're a very similar solution. So what you do is you take e to the natural log of 2x and e to the 2.4. But e to the natural log of 2x is just 2x. And on the right hand side you have e to the 2.4, which you can plug in a calculator. So x is equal to e to the 2.4 power divided by 2. So e to the 2.4 divided by 2 is 5.512. And if we go back to the original equation and we take the natural log of 2 times 5.512, we should get 2.4, which we do. Okay, 82. Here we have log to the base 10 of 3z is equal to 2. Well, here we could use e as the base because we had e in the natural log, which is to the base e. Here we have to use whatever the base is with the logarithm. So since it's log to the base 10, we have to raise 10 to that power. So it's 10 to this and 10 to that. But 10 to the log base 10 of 3z is just 3z. 100 squared is 10 squared is 100. Divide by 3 and you get 33.33. And we can do log base 10 on our calculator, so let's do that. So log base 10 of 3 times 33.3, which is 100. Log of base 10 of 100 is 2. Okay, next one, 83. So you've got 6 times log to the base 3 of 0.5x equals 11. So divide both sides by 6. So you get 11/6. And then you make these the exponents. So it's 3 to the log base 3 of 0.5x is equal to 3 to the 11/6 power. The left-hand side, 3 to log base 3 of something is just the something. And then you raise 3 to the 11/6 power. Make sure you put those in parentheses so that you're not raising it just to the 11th power. So you'll get 7.494, and x is this divided by 0.5 or multiplied by 2. So I'm just going to multiply by 2, and I get 14.99. If I plug that back in here, I'll have, well, yeah, the calculator won't do log base 3. You'd have to use change of base formula. So we'll just assume we did it right. (84) 5 log base 10 of x minus 2 equals 11. Okay, same thing. Divide both sides by 5. Then you have 10 to the log base 10 of x minus 2 is equal to 10 to the 11/5 power. 10 to the log base 10 of x minus 2 is just x minus 2. and 10 to the 11 fifths is going to be over 100 because 10 fifths is 2, 10 squared is 100, so we get 158.489. Add 2 to both sides, you get 160.489. This one we actually check because we have log base 10 in our calculator, so we take 5 times log of 160.489 minus 2, right parenthesis, and we get 10.9999999, which is close enough to 11. Okay, 87. Natural log of the square root of x plus 2 is equal to 1. So you're going to rewrite the square root as a fractional exponent. That allows you to bring that outside. And then we can multiply both sides by 2. So we get natural log of x plus 2 equals 2. Then you would do the e, because it's the natural log, the base is e. So e to the natural log of x plus 2 equals e to the second power. E to the natural log of x plus 2 is just x plus 2. So x is equal to e squared minus 2. Subtract 2 from both sides. And that is, so you take e squared minus 2 is 5.3891. And if I plug that back into my original thing, so I use my calculator, the natural log of the square root of 5.3891 plus 2, 1 right parenthesis, 2 right parentheses, I get 1.00000. Okay, 92. Get the natural log of x plus the natural log of x plus 1 equals 1. So we're going to combine these two into a product. Then we can use the inverse properties of logarithms and exponents. So these become the exponents. E to the natural log of something is that something. And over here we have just e. So if we multiply at the left-hand side, we get x squared plus x equals e, or x squared plus x minus e equals 0. So we could use completing the square, we could use the quadratic formula. Let's use completing the square. So you'd have x squared plus x minus e. So the coefficient in front of the x term is 1. So we take 1 divided by 2 and we square it. So that's 1/4. So we add 1/4 and we subtract 1/4 to balance that out. And then we make this into a complete square, which would be x plus 1/2 squared. And then this stuff can move to the right-hand side. So you'll have e plus 1/4 instead of negative e minus 1/4. Then you would take square root of both sides, plus or minus the square root of e plus 1/4. And then we would subtract 1/2 from both sides. So you get plus or minus 1/2 times the square root of e plus 1/4. And let's just see what those numbers are. So I'm going to use negative 0.5 plus the square root of e, so that's just e to the first power, plus 0.25, right parenthesis, enter. So with the positive square root, I get 1.2229, and the negative square root, I get negative 2.2229. So let's plug that into the original equation. So the natural log of 1.2229 plus the natural log of 1.2229 plus 1 should be equal to 1, which it is. Okay, let's try the other one. So the natural log of negative 2.222, we can't take the natural log of a negative number. So that one's not valid because the domain requires x to be greater than 0, or this argument to be greater than 0. So it's just the one solution. Okay, 94 natural log of x plus, yeah, this is very similar to the last one. Get the right numbers in here. Okay, combine using the product rule like that. Then you do e to the natural log of x times x plus 3, e to the first power. So e to the natural log of that is just x times x plus 3. On the right hand side we have just e. Multiply about left hand side, x squared plus 3x. And I'm going to leave e on the other side. So again, you take 3 divided by 2 and square it. So that's 9/4. So we add 9/4 over here as well. Make that into perfect squares, so it'll be x plus 3/2. Quantity squared is equal to e plus 9/4. Take the square root both sides, plus or minus the square root of e plus 9/4. X is equal to negative 3/2. And we're only going to do the plus square root because the negative square root is going to give us a negative number, which we found out from the previous problem. It's not one of the solutions because it's going to give you a negative argument. Okay, so we have negative 1.5 plus the square root of e, which is e to the first power, plus 9 divided by 4. And I get 0.72896. So if I try that, the natural log of 0.72896 plus the natural log of 3.72896, so that's adding 3, and I should get 1, which I do. Okay, one last one here. The natural log of 5, x plus 5 is equal to the natural log of x minus 1 minus the natural log of x plus 1. Okay, let's move everything to one side. So the pluses become minuses, the minuses become pluses. Then we can combine those together. So you get the natural log of x plus 5 times x plus 1 divided by x minus 1 equals 0. So then you'd say e to the natural log of this whole thing is equal to e to the 0 power. E to the 0 power is 1. And the left-hand side just becomes x plus 5 times x plus 1 divided by x minus 1. So this argument here becomes that. So then you can multiply both sides by x minus 1. So you'll get 1 times x minus 1. It's x minus 1. You'll multiply out the left-hand side, which will be x squared plus 6x plus 5 equals x minus 1. Move those to the other side. So this becomes negative x plus 6x will give you 5x. And 5 plus 1, when this goes to the other side, it becomes positive 1. You get 6. And you can factor that. You get x plus 2x plus 3 is the factor. So the two solutions are x equals negative 2 and x equals negative 3. The problem is that those are going to result in negative arguments. And so those are solutions, but they're not real solutions. So they're not in the domain. So there are no solutions to that particular problem. And because I wasn't expecting that, I'm going to just look in the back of the book and see what is the answer. So this is chapter 3, section 4. Chapter 3, section 4, problem 95, no solution. That's what I just said. Okay. So we came out with answers, but because the answers are not within the domain, in this case, x has to be greater than 1 so that this term is positive. If x is greater than 1, these two are positive, so that one's the limiting one. So this says no solution. In the previous problem, we had two solutions mathematically, but only one of them was actually a solution because of the domain of the original equation.